Today I'm going to discuss about how to find out the regression equation, that regression equation on which we worked yesterday, that regression equation which was developed on the basis of certain problems where the response variable and input variables were given. This regression equation will be deduced in its general form with the help of method of least squares. So today I'm going to discuss with you about the analysis which is called method of least square and how to use this method to get the two lines of regression. Once this method is clear to you, then you will be able to understand various other aspects which are apparently not clear from the practical application of the regression equation. So I'm going to start my today's session with the discussion on the derivation of regression equation by the help of method of least square. And it will take some time and I'll go very slowly because right now I'm not going to solve problems. I'm going to do mathematical analysis. We know that if the variable which we actually call as response variable and the variable x which we known as input variable, if these two variables are given, sometimes input variables are called explanatory variables also, then we can set a line of regression of the following form. In general, the line of regression between the two variables is taken to be this. Okay, where this quantity epsilon is the error term. And in the morning session, I have already told that why this error term, the mean of this error term is 0. If you go through my first video of today's morning session, then you will get to know that why this error term, mean of this error term is 0. That has been explained over here. Now you see that if I assume that capital Y and capital X are linearly connected, which we can guess by seeing the scatter diagram of the plots of capital Y and capital X, then we can assume a relation like that. Okay. But unfortunately, this alpha and beta here actually are not known. We do not know what are their values. And we can fit several straight lines with respect to capital Y and capital X according to the choice of the parameters alpha and beta or the constants alpha and beta. If you put alpha to be 2 and beta to be 3, then you will get an equation of the form y equal to 2 plus 3x with some error term in it. But putting any value to alpha and beta and getting the regression line will not be a good solution to the given problem. We have to have some kind of mathematical analysis so that we can find the best fit of, or I can say rather, best linear fit of y and x. Since alpha and beta can have infinitely many values, out of these infinitely many values, to find the best estimate of alpha and the best estimate of beta is a very tedious job. So we have to go through an analytical procedure by which we can find this out. And that analytical procedure is actually known as method of least square. Since alpha and beta are not known, so we shall estimate alpha by an estimator which is called alpha, which is denoted by alpha cap. And let us, without any loss of generality, let us name this estimator by capital A. And the estimator of beta, since beta is unknown, is denoted by beta cap, and let us name it as capital B for the simplicity, for the sake of our calculation. And we will choose these estimators in such a manner, or we want to choose these estimators in such a manner so that the sum of the error terms, square of the sum of the error terms is minimized. We want to do this in such a way so that the square of the sum of the error terms is actually minimized. Okay. Now, why do we need to calculate the square of the sum of error terms? We could have considered the sum of the error terms only. It is because it may so happen for certain data that the sum of the errors are actually minimized, is having some minimum value, but individual values for the variable capital Y and capital X may be very large. What is error actually? Error means the difference of the observed value with the theoretical value. That is we know as error. Now, if we consider the sum of these errors, it may so happen that this sum is actually minimized, but these individual values are maximized. So to analyze it properly, we need to take the square of the sum of this error, and we'll try to minimize that. So what is this error over here? This epsilon, if I choose this epsilon to be error term, so we can write from this particular section, we can name it as equation star. From equation star, we can write the equation to be y, estimate of alpha plus estimate of beta into capital X plus the error term epsilon. Now, according to our choice, estimate of alpha is A, estimate of beta is B, and the error term is this. Now, this implies this error term can be expressed as y minus A plus B X. So y is the observed value. This is the observed value. And this is the theoretical value, which will be obtained from the equation by putting different values for capital X. This is our epsilon. Now, since capital Y can take various values at different points of time, suppose at one point, capital Y is taking the value yi. Now, this yi I am writing in capital letter. Remember, this yi is not a unique value. This yi is itself a random variable. Try to understand this point. Suppose we are doing the experiment in the first month. Then my random variable is y1. The response variable is y1. And my input variable is x1. If I am doing the same experiment in the second month, my random variable is y2. My input variable is x2. And so on. But the meaning of the random variable and the meaning of the input variable, they are actually same. Say, for example, each semester, I want to study a correlation between students' performance and the study hour of the students. Is there any sort of correlation between these two? We repeat the process every 6 months. So in the first semester, when the student is in first semester, I have collected the data of the students' study hours and their performance in the semester examination. we name these two variable as y1 and x1. Similarly, when the student is in second semester, I did the same, and so on. So each of these things are actually random variables. Do not think that I'm writing the elements of the random variable capital Y and capital X. So if I do so in this manner, then we can express the equation which is written in terms of epsilon as follows. For each of these cases, for each of these experiments, epsilon i's, each time the error term is calculated and it is found to be yi minus a plus bxi. Now, method of least square is saying that you have to consider the square of the sum of the error terms. Okay, so we take the summation of the error terms. Now, in my case, the experiment which I want to perform, a student completes an 8-semester course in his while he is in his undergraduate program. So I have to do the experiment 8 times in each semester. Since here in general I'm going to repeat the experiment on the basis of the response variable y and on the basis of the input variable x several number of times. So we consider that number of times to be small n. So here the number of times is small n. N number of times I'm going to repeat this experiment. So I will run my subscript I from 1 to up to small n. And I'm considering the error term. Not only this, I'm not taking the summation of the errors. I'm taking the square of the sum of the errors. Sum of the squares of the errors actually. So if I do so, the right hand side will take the following form. You see, it will take the form yi minus a plus bxi whole square. So this I want to minimize so that I get the best estimate denoted by capital A and capital B. And if once we can find the value capital A and capital B, then we can substitute that value in the equation and we'll get our best fit, which will be known as the linear regression equation. We give this equation a number. Okay, let me simplify this equation a little bit. We can write it as I goes from 1 to n epsilon I square. This is equal to summation I goes from 1 to n yi minus a minus bxi whole square. Now remember one thing, that here, if we want to minimize this particular term, then I have to take the help of the extremization problem. And in extremization problem, to apply the extremization problem, we find that this quantity, which I have highlighted by blue color, this quantity is actually a function of 2 variables. One variable is capital A and another variable is capital B. Do not treat yi and xi to be the variables here. Here capital A and capital B are the variables because we do not know their values. And yi and xi, these values are on the other hand, these values are known to us. So if I want to minimize this quantity, this error term highlighted by blue color, what we need to do is that we have to consider its derivative, its partial derivative with respect to capital A and with respect to capital B as well. And those partial derivatives should be equated to 0. For simplicity, I am naming this expression as capital E. Otherwise, each time I have to write the entire big expression under the summation sign. So we are naming this as capital E, just for the sake of our calculation. Since we want to minimize this quantity with the extremization theory, we can take the partial derivative of E with respect to capital A we will equate this to 0, and we will take the partial derivative of E with respect to B and we'll equate it to 0. This implies, now I'm going to take the derivative of this. So first of all, we will get this quantity twice summation I goes from 1 to n yi minus a minus bxi, and the derivative of a with respect to a, derivative of minus a with respect to minus a will give you -1, and that will be equal to 0. And we can write it as summation I goes from 1 to n yi minus a minus bxi, this is equal to 0. Similarly, if I want to take the partial derivative of the second quantity, that is partial derivative of E with respect to B, we get, first of all, we get twice summation I goes from 1 to n yi minus a minus bxi, and then partial derivative of minus bxi with respect to b, which gives us minus xi, which is equal to 0. And from there, we can write it as, this implies summation I goes from 1 to n yi minus a minus bxi, which will be multiplied by xi, this is equal to 0. So after taking the partial derivatives of the error term, we are getting these two expressions. By further simplifying the expressions, simplifying the equations, we get, from the first equation we are getting summation I goes from 1 to n yi minus or equal to summation I goes from 1 to n capital A plus summation b is a constant quantity which is independent of I. So I goes from 1 to n summation xi. This is the quantity which I get. This is the term which I get from the first equation. Okay. So we can name this equation as equation number 1. From this one, from the second partial derivative, we get summation I goes from 1 to n yi, that is equal to summation I goes from 1 to n. A is constant quantity independent of I. A is variable. We want to find A, but A is independent of I. So we write A into summation I goes from 1 to n xi plus B I goes from 1 to n summation xi square. We name this equation as equation 2. Now, I am considering A to be unknown. That doesn't mean that A is variable, because you see, if there is a linear relationship between the two variables, such as the student's study hour and student's performance in the semester examination, that doesn't mean, and if I repeat the experiment 8 times during his 4-year courses, that doesn't mean that if there is a kind of linear relationship between these two variables, it will keep on changing from experiment to experiment. The linear equation will remain same. Some variations may be here and there, but the ultimate equation will not be. A kind of relationship will be obtained. Now, if the student stops studying, he will be deviated from the straight line. That is a different issue. But equation is not supposed to be changed if everything goes well throughout our experiment. So therefore, capital A and capital B is constant. And therefore, I'm repeatedly saying that A is constant, we can take it outside the summation sign. Do not confuse yourself that sir is telling on at one point, sir is telling that capital A is unknown, and on the other hand, he is telling capital A is constant. A constant may be unknown, isn't it? So this unknown that we are going to find over here. Now try to look at this equation. We will talk about this equation later on. This equation that we have obtained are actually has a name. This set of equations has a name, and these are called normal equations. These equations are actually known as normal equations. Okay, and these equations we have found with respect to the straight line y equal to a plus bxi. Remember, with respect to this straight line, we have found this equation. Now we shall divide equation 1 by n. What do we get? We will get 1 by n summation I goes from 1 to n yi. This quantity is na, that will be divided by n, and here we will write b summation xi, I goes from 1 to up to n by n. From there we can write it as y bar is equal to a plus bx bar. This is a very important relation. You just note it down. What this relation is saying? This relation is saying that if you try to get the best fit between the variables capital Y and capital X, then the average value of capital Y and the average value of capital X is supposed to pass through that particular line. So this is a very important relation that we have obtained from the first normal equation. Okay, and okay, I have missed one particular factor over here in the equation 2. One xi is present over here. Remember, I missed this xi. Xi is getting multiplied by yi. Okay, now we shall deal with the second equation. We will divide the equation 2 by n once again. Let us try to find what comes out of it. If I do so, we will get 1 by n summation I goes from 1 to n xi yi, a summation I goes from 1 to n xi by n plus b summation I goes from 1 to n xi square by n. Okay, these are the things that we are getting from here. Now we can rewrite this equation in the following manner. This is equal to 1 by n summation I goes from 1 to n xi yi is equal to a x bar plus b 1 by n summation xi square I goes from 1 to n. Remember that covariance of xy has a computational formula of the following form. It is given by 1 by n summation I goes from 1 to n xi yi minus x bar y bar. This is the computational formula for covariance xy. And computational formula for sigma x square is of the form 1 by n summation I goes from 1 to n xi square minus x bar square. So if I try to use these equations over here, the given equation can be rewritten in the following form. In place of 1 by n summation I goes from 1 to n xi yi, I can replace this by covariance xy plus x bar y bar is equal to ax bar plus 1 by n summation xi square will be replaced by sigma x square plus x bar square. So let us call this equation to be double star. Okay, we are calling this equation to be double star, and let us call this equation to be single star. Now I'm going to the next page. Okay. So in the next page, what I'm going to do is that I will subtract from double star, from equation double star, x bar multiplied with equation single star. What does this mean? I mean to say that I am going to multiply equation star by x bar, and that equation will be subtracted from the equation double star. Okay. So let us do it. First of all, I'm going to write the equation double star once again. So it is covariance xy plus x bar y bar is equal to ax bar plus b into sigma x square plus x bar square. And when we multiply star by the quantity x bar, then we get x bar y bar is equal to ax bar plus bx bar square. Bx bar square. Now I'm going to subtract the equations. So left hand side gives me covariance of xy. Right hand side, ax bar will cancel with ax bar, bx bar square will cancel with bx bar, and we will get b sigma x square. We will get b sigma x square. From there, we find b to be covariance of xy by sigma x square. Okay. But we know that correlation coefficient between x and y is equal to covariance of xy by sigma x into sigma y. So this implies that we can write correlation coefficient xy multiplied by sigma y as covariance of xy by sigma x. We can write b to be covariance of xy by sigma x into sigma x. Now in place of this quantity, we can substitute this one. So we can write rxy into sigma y by sigma x. Now you see, you are getting your regression coefficient. This form of regression coefficient is actually known to you. What was my equation? My equation was y a plus bx. This was my equation. Remember, I am not writing the error term. The original equation was like this: y equal to alpha plus beta x plus epsilon. But I am estimating alpha and beta by capital N, capital B, so that the term epsilon is so small, the sum of the squares of the sum of the squares of certain quantity, if very small, then the quantity itself is very small, which is negligible. So that epsilon, if I write the equation in the following manner, that epsilon will be negligible. So that's why I'm not writing the error term over here. We know that we had the equation y bar equal to a plus bx bar. That equation we also obtained. Now from there, the quantity a can be written as y bar minus bx bar. So I'm going to substitute the value of a from this and value of b from that. Let's see what we get from this simplification. So we are going to write y minus bx bar plus r into rxy into sigma y by sigma x into x. This implies y minus y bar is equal to, oh, one more thing. In place of b, you can resubstitute this, or you can do one thing, because this quantity b and that quantity, they are actually same. So there was no need to rewrite b in this particular form, or you can write b in this form, whatever. B is being taken as common, and we are writing this as x minus x bar. Or you can resubstitute the value of b, and you can put r into sigma y by sigma x into x minus x bar. This is the regression equation of y on x. And it is also showing us that the average value of the response variable and the average value of the input variable passes through the point. So one regression equation y on x have been derived. I'm not going to derive the second regression equation, but I want to make a point over here. What is the point? The point is that as I told you in my previous class, that you cannot just interchange the positions of y and x to get the regression equation of x and y. It is not right. What we do to find regression equation of x on y is that we assume in a similar manner a line of best fit given by x equal to a prime plus b prime into y. And we use the same set of analysis. We apply the same set of analysis on this equation, which will in turn yield the regression equation x minus x bar r into sigma x by sigma y, y minus y bar. So remember, these two analyses are actually very different from one another, because the assumption of the line will be different from one another. Here we are assuming that for the regression equation y on x, we are assuming the line to be y equal to a plus bx, and for the other one, we are assuming the line to be x equal to a plus by. Okay, I will ask you to try this, try to find out this result by yourself later on. Okay, so therefore there are two lines of regression. So, and this line of regression is actually telling you, giving you the line of best fit. Why it is called the line of best fit? It is because of the following scenario. Suppose we have certain points given as follows. These are the points. Okay, these are the points. Now, if I ask you to draw, okay, let me draw the points clearly so that you can see it. We know that some sort of a linear tendency is there, hidden inside the point, and the variable x, when increasing, the variable y is also increasing. Now, if I ask you to draw the straight line, you can do it in various ways. You can assume the straight line in this manner. You can assume the straight line in this manner. You can assume a straight line in this manner. You can assume a straight line in this manner. The line of best fit will be that line where two scenarios may happen. First scenario is that most of the points of the response variable and the input variable will fall on the line, or the deviations of the points around the line of best fit is very minimized. because that is how we actually calculated the line of best fit. Not therefore, in the previous class, I told you that not every line is line of best fit, but line of best fit is obviously a line. Okay, so therefore, every regression equation is a straight line equation, is a linear equation, but not all linear equation is regression equation. And you will get to see that this particular fact with the help of an example that I'm going to demonstrate in my next session. Okay, here is a problem for you, a quick problem for you. Two regression equations actually are given, 5 plus 2.8 into x. They are saying that this is the regression equation. This is the regression equation of y on x. Another regression equation is given, which they are claiming to be have the form x equal to 3 minus 0.5 into y. They are saying that this is regression equation x on y. So they are asking that whether their assumption is correct or not. Can they consider that this equation to be the regression equation of y on x and this equation to be the regression equation of x on y? A quick analysis will help us to find that. With respect to first equation, the regression coefficient is 2.8. And with respect to the second equation, the regression coefficient is minus 0.5. Now, the product of these two regression coefficient, whatever the value is, will be negative. And we know that that is the product of two regression coefficient is actually correlation coefficient squared. This is very absurd. So I mean, that statement about these two lines of regression, that one is y on x and another is x on y, is actually not correct. That is how you can analyze the things with the help of regression equations. We are going to continue in the next class.